What up, people? So today, this video is about hybrid orbitals. You know what? I'm not even gonna, I will write it for you guys. Hybrid orbitals. So I know that a lot of you guys weren't here for class today because of some club photos. So hopefully this video will help. So hybrid orbitals is our last topic for this unit. And the general definition, okay, just gonna throw it out there. The general definition, so write this in your notebooks if you weren't here, is when it's hybrid orbitals are two or more orbitals that join together. Okay, two or more orbitals that join together. Okay, and we know that from last unit that there are s orbitals that exist. We have p and then d and f orbitals. Okay, so hybrid orbitals are when two or more orbitals join together. Now we're going to talk about why they join together in a bit. So let me just Control Z this up. Okay. So the best way to kind of explain this, I think, in my personal opinion, is to give you guys an example. So let's choose a nice brush over here and let's begin. Let's choose a size and let's go. All right, so let's do an example with CH4. Okay, methane. I love this example because methane is it's a very simple molecule to draw. Okay, so we have C. You know what? I'm gonna draw it over here. So we have H is on the outside, C in the middle, H over here, H over here, H over here. I think my mouse pointing skills are very good because of StarCraft. Anyways, let's go on with hybrid orbitals. So here we have a drawing of methane, CH4. Now I want you to nod while you're watching this video in front of your computer screens or your iPhones or however you're watching this video. Nod if you agree this is the correct Lewis structure. Okay, if you're not nodding, then please come see me tomorrow and we'll talk about it. Okay. And would you guys agree that these bonds over here, this carbon and hydrogen bond, this carbon and hydrogen bond, this carbon and hydrogen bond, and this carbon and hydrogen bond, all these bonds, would you agree that they're the same? Okay, if you're not nodding, please come see me tomorrow. Yes, they are indeed the same. These are all single bonds, okay, between this carbon and the hydrogens outside. They're all the same, these four bonds. But now let's kind of look at the carbon's electron configuration. Okay, the center atom's electron configuration. The hybridization, hybrid orbitals are always referring to the center atom. Okay, because the center atom is responsible for all the other bonding. Okay, and of course there may be more than one center atom for bigger molecules. Anyways, the electron configuration for carbon is double gas helium, and we have 2s 2p 2. Yeah. If you think this is the correct electron configuration for carbon, please nod. If not, come see me tomorrow. Okay, so we can see that there is 2 electrons here, 2 electrons here. So 2 valence electrons and 2 valence electrons. So there's 4 valence electrons total. And we know that carbon has 4 valence electrons. So if we take a look at the structure over here, there's 4 valence electrons around carbon. And it makes sense because there's 4 hydrogens around. So one of these electrons, okay, and this bond belongs to hydrogen. One of these electrons belong to carbon. Same for this bond, and this bond. So this works. But now let's take a look at the types of valence electrons. So we have 2 that come from the 2s orbital and 2 that come from the 2p orbital. Okay. Now, if all of these bonds, these 4 bonds, were identical, then this kind of doesn't make sense because the p orbital has a higher energy. Okay. These bonds are identical in strength. The p orbital has a higher energy level, so this kind of doesn't make sense. So let's draw the orbital diagram. So if you guys remember what this is, hopefully you do. You have s orbitals and the p orbitals. Okay, there's 4 electrons or 2 electrons in the s. Okay, and there's 2 electrons in the p. Okay, so I'm gonna erase the other stuff. I'm gonna erase the bottom over here. So take a look at this. Okay, take a look at the orbital diagram. And I want you to notice that I'm erasing this. But I want you to notice in the orbital diagram here that two of the electrons come from S and two of the electrons come from P. Now this doesn't even make sense because there's two electrons that are already on the S and there's only two single electrons on the P. Okay, so then you have to think about how are we going to get four equal electrons. Okay, the way to do that is to combine these orbitals. So if I combine the S and the P to make, S and P orbitals like this, and we have four valence electrons for carbon. Check this out. Now all four electrons, okay, are equal. They're part of a hybrid orbital that has S and P orbitals in it, and they're alone. So these four all belong to carbon. They're alone, so they can accept four bonds. Okay. So the electrons around carbon belong to a hybrid orbital between S and P. And we call this particular orbital for carbon, sp3. Yeah, sp3. Why? Because we have an s orbital here, and we know that the p orbital has three orientations like so. So we have one s, okay, so we have the s, and we have the first p, the second p, and the third p, so sp3. So all the electrons, all the valence electrons around carbon come from the sp3 orbital. Okay. Now let's take a look at another example. Okay. Let's take a look at this Si6. Sorry about that. Please excuse my dog. So let's take a look at Si6. Now if you draw this out, I'm going to draw it out really quickly. 1, 2, 3, 4, 5, and 6. And there's iodines. Ooh, this is a very bad drawing. Please try to make this look a lot more symmetrical if you can, you guys. This is generally Si6, okay? And I'm not going to draw the lone pairs. I know you know. You know what? I already started drawing the lone pairs, so I will draw the lone pairs for you guys. Okay, oops. Okay, and 1, 2, 4, 5, 6. So one more lone. Okay, and let's move on. So we have Si6. Now, you agree this is correct? It is correct. Please nod. We know that each of these bonds between sulfur and iodine, they're all the same, all 6 of them. Let's take a look at the electron configuration of sulfur. We have neon with a bracket, and we have 3s2, 3p4. Okay, so 6 valence electrons. Now let's draw the orbital diagram. Okay, p and s. Okay, there's 6 valence electrons, or 2 in s and 4 in p. Now, similar to carbon, this does not make sense because these 6 bonds are the same. So we need to create some kind of hybrid orbital. Now, if I were to combine the s and p, that's your first intuition. And, if I were to combine the s and p like so, and have 6 electrons, this doesn't make sense because we have two orbitals that are already filled. So these guys can't even bond. And we only have 2 leftover singular electrons that can bond. This picture shows 6 iodines bonding, so this really doesn't make sense. So what we can do is expand onto the d orbital. Remember, the d orbital has 5 more orbitals, 5 more orientations. Okay, so what we can do is this, you guys. We can combine the s, p, and the d orbitals. So what am I going to do? Hybridize. 1, 2, 3, 4, 5. Okay, so it's 5 plus 3 plus 1 is 9. S is here. These are the p orbitals, the d orbitals. And we created a hybrid of s, p, and d orbitals. Now let's try to spread the 6 electrons across. Okay. This makes sense. So now all of these guys have the same type of electron, and all of these bonds are equal because it's a hybrid um, the electrons come from a hybrid orbital from between amongst S, P, and D. In this case, we call this the sp3d2. Why? Because we have one s here, and then we have three p's over here, and we have two d orbitals that are being used. So sp3d2. Now we can make it, and this is an explanation, and honestly, you're not responsible for this explanation. This is just something I'm fascinated by, but you are responsible for figuring out hybrid orbitals, and there is an easier way to do this, and it's simply we know that the biggest shape we can have, or the largest number of attachments an atom can have, is 6, or an octahedral. Okay, so we know the max hybridization of any center atom is going to be sp3d2. Okay, so how we calculate hybrid orbitals is take the center atom and count the things around it. These things can be lone pairs or lone atoms. Okay, so let's say we have some kind of center atom over here. We call it cent, and we have one attachment, whether it's a lone pair or an atom. If we have one attachment, this falls into the s orbital. So we call this s hybridized. Okay, it's not even really a hybrid orbital. If you have two attachments, we call this the sp, because we suddenly go into the p orbitals now. Okay, sp. If we have three attachments, we call this the sp2, because we use two of the p orbitals. If we have four attachments, we have sp3. And then once we get to 5, 6 attachments, we go into the D region. So if you have 1, 2, 3, 4, 5 attachments, we have the d orbital. So we have sp3 d1. If we have 6 attachments, whether it's a lone pair or an atom, this X can be a lone pair or an atom, then we have what's called sp3d2. Okay, so it's already been 12 minutes, you guys. So let's just do a quick example, and you can ask questions tomorrow. So let's just look at water, our favorite element, water. Okay, lone pairs like that. Center atom is oxygen. Let's count the things around it. We have 1, so S. We have 2, 2, so we have P. We have 3, so sp2, and we have 4 attachments, so sp3. Okay, so this would be all these electrons around oxygen are sp3 hybridized. Okay, that's all it is, you guys. So on your review worksheet where it says hybridization, you're going to tell me for water that it's sp3. Okay. All right, the video's been long. Thank you so much for watching, you guys. You guys rock. You're awesome. Best chemistry students in the world. Thank you.